Hello
Hello.
everyone. Welcome back
Welcome.
to a series of live discussion. Let me once again welcome Mr. Ashwini Kumar Sanaji and Suresh Dwivedi. Today we are going to talk about when to use Zener diode regulators in power when to use Zener diodes versus voltage regulators in power supplies and how to make your bill of material more cost effective. So my first question is, what are the basic principle of operation of your Zener diode and voltage regulator ICs?
Hello. The basic principle of operation of the Zener diode is first we have to consider the Zener breakdown voltage. Zener diodes are designed to operate in a reverse bias mode. When the reverse voltage across the diode reaches a certain value called the Zener breakdown voltage, the diode starts conducting in the reverse direction without being damaged. So general breakdown voltage is sharp and precise to make the general diode ideal for voltage regulation. Also, voltage regulation is very important. Once the general diode reaches the voltage, it maintains a constant current across the terminal despite change in the current through the diode. Means in this case, current is constant. This makes it useful for maintaining a stable reference voltage. There are various applications of this type of operation of the Zener diode: voltage clamping, voltage reference, and center regulators, etc. etc. Now, for the principal operation of the voltage regulator, ICs are entirely different from the operation of the Zener diode. In this case, we have to note the types of voltage regulator. There are various types of voltage regulators available, such as the linear regulators. In the linear regulator, provides constant output voltage by dissipating excess power as a heat. And the switching regulators, which are the very high frequency switching, and components like inductor and capacitor are used for improving the efficiency of the voltage regulator. Another is in case of linear regulators such as 780, 780, 12, 780, 15, etc., etc. These are the positive regulators. Similarly, on the other hand, there are negative regulators like as a 7905 5 volt negative, 7908 minus 8 volt, 7912 minus 12 volt, etc. etc. Such type of the linear regulators. In these type of the operation, they operate by adjusting the resistance of the pass transistor to drop the excess voltage. The feedback mechanism maintains the output voltage. Typically, such type of the transistors pass the error amplifier and the reference voltage sources. So it has a very good efficiency. And comes on the switching regulators. Switching regulators used as a buck boost and buck boost converter types. So in brief, you may say that the buck converter steps down the input voltage to a lower output voltage. Boost converter is step up to the input voltage to a higher output voltage. And in both buck boost converter can step the input voltage up to a down voltage. Comes on the it has also a regulation mechanism, protection features also included in this one. For the comparison of the Zener diodes versus voltage regulators, then income Zener diode, it is a simple and cost-effective low power application and suitable for providing a stable reference voltage and limited to the lower power application. Means Zener diode based power supply is used for the low voltage application. While in case of the voltage, it is more complex and versatile, can handle higher current, higher power with better efficiency, especially switching regulators, and provide more precise and stable output voltage with the integrated protection. So these are the basic principles of the Zener diode based power supply and the voltage regulator based power supplies.
So can you explain the key difference between the two?
What?
Can you explain the key difference between the two?
Yeah, sure. Here, main key difference in the Zener diode as regulator power supplies are the simplicity. In the in Zener diode circuits are simple, typically require only one Zener diode and a current resistor only. There are two components, so it is very simple and easy to design to the low power application with the minimal components. Surely its cost will reduce to generally lower cost due to the components needed. Because it used only two components, diode as well as resistors. Cost effective for simple low power regulations need. And its efficiency less efficient because excess voltage is dissipated as a heat in the current limiting resistor. Suitable more for more suitable for the low current and the low power application. And it provides a single fixed output voltage determined by the Zener backdown voltage. What is the backdown voltage of the Zener? That is your output in this case. Limited flexibility in adjusting output voltage without changing the Zener diode. And current handling, limited current handling capacity is typically suitable for the low current. Can overheat if the current is too high, requiring careful consideration of the power. And these are the Zener diode based power supplies key qualities. And on the other hand, when we are discussing about the voltage regulator, so it is a complex circuit. It is more complex than the Zener diode power supply, but still relatively it provides a good power supply. Simple but with a few external components like capacitor etc. to avoid the ripples etc. And it often includes additional features like thermal shutdown, current limiting, and the short circuit. In this case, we use a power supply heat sink. When voltage is excess, it automatically switches off. That is the thermal shutdown. Similarly, its cost. It is more costlier than the general diode-based power supply. Higher initial cost for the IC, but potentially lower overall system cost due to reduced need of the external component and heat sink. Application cost effective for more complex and the high performance regulation. It has better efficiency. Linear regulators are dissipate excessive voltage and heat similar to the general diode. However, switching regulators are much more efficient. And the voltage range, many voltage regulator ICs offer adjustable output voltage. There are two types of voltage regulator. One is a fixed voltage regulator and another is a adjustable voltage regulator. So it has a very good range from 0 to another depending on the voltage regulator you are using so far. And the current handling capacity designed to handle higher current with the built protection circuits. So these are the key differences. So in the brief, you may say best general diodes are the best for the simple low power application where cost and simplicity are the critical, limited in precision, efficiency and current handling. While in the voltage regulator case, ideal for more complex, higher power application requiring precise regulators, higher efficiency. These are the qualities of the voltage regulators.
Okay. So, what are the advantages of voltage regulator IC and Zener diode?
So, as per the Zener diode and the voltage regulator, both carries their own advantage and some sorts of disadvantage in the design. So, suppose that if you use the voltage regulators in the circuit, then it will provide you more precision, the higher range, and the thermal management, and some extra features like already the Suresh sir have told us that they also provide the extra facility like the thermal management, the automatic shutdown, overcurrent protection, and all those things. So if you use the voltage regulator in the circuit, then it will be more precise regulation, and if your circuit need more precise voltage regulation system, then in such a scenario the voltage regulator is best for your design. So voltage regulator provide you best precision, efficiency, and also the larger range of the voltage regulation. It will give you the large range in the same IC by configuring the different capacitors and resistor. It's the same IC provide the wide range, and there are in a wide range the ICs are available to regulate the voltage. Like if you want to regulate the voltage from 0 volt to 12 volt to the 5 volt as a output, then you have the large range. Like you have the 0 volt, you have the 1 volt, and 100 volt. Then it will convert all those into the particular range, not 0 volt, sorry for that, between the range of 5 volt to 12 volt. So it have that wide range. But if you have the Zener diode, then the range is very limited. It's regulate power to up to few decimals or few voltage only. But the voltage regulator provides the wide range. So this is advantage of the voltage regulators. When you use the voltage regulator, is always provide the high precision, wide range, and extra features like thermal management, the current over current protections, and thermal shutdown, and all those things. But in the Zener diode, if you see the Zener diode, it also consists their own and sort of the advantage over the Zener diode, over the voltage regulator. Like Zener diode, if you use the Zener diode, the circuit is very simple. It provides you the simplicity in the circuit, and also it is cheaper than the ICs of the voltage regulator IC. Like if you are using the voltage regulator IC, you often also need the capacitor, two capacitor from the both side, and the IC as well. So IC itself cost you around 1 to 3 rupees, and then the capacitor again cost you around 2 to 5 rupees. Then the overall cost of that whole bill of material is around 10 rupees. But while if you are using the Zener diode, might cost you 1 rupee the Zener diode, and 1 to 2 rupees register. So if you use the Zener diode, it gives you the advantage of the simplicity in the circuit, and also give you the advantage of the cost of the whole system. So these are the two things that both have their own advantage. One provide the larger range, the more precision. One provide the simplicity, but and lesser bill of material.
So, what are the challenges you face when you use voltage regulator IC or a Zener diode?
So challenges, if you use the suppose that if you use the Zener diode, then one of the challenge that you face, the range, it didn't provide you the wider range of the voltage regulation. So if you're designing a circuit that need a wider range of voltage regulation, that the fluctuation is very high, range of voltage is very high, then you have to use the voltage regulator. And the second challenge is that if you use the Zener diode, the second challenge that you face is the power dissipation. These Zener diode also always dissipate the power a lot, and it sometimes it get overheat, and also failed due to the overheating. And there is another challenge is the temperature. It didn't provide you the working accurate working in the temperature fluctuation, where the temperature fluctuation is very high, or where the temperature is very high. So whenever the Zener diode is basically what the PN junction, what you see inside the diode, the PN junction. And when the temperature is very high, when you heat up the diode, the PN junctions atoms in the PN junction will sometimes you know get passes from one junction to another junction. So if you use the Zener diode in the circuit and the temperature fluctuation is very high, so they are not very good for the high temperature and very low temperature or very frequent temperature exchanges. But so this is the another challenge that you face in the circuit in the with the Zener diode. One is the temperature range and one is the voltage range, and third is the efficiency as well. Zener diode didn't provide you that much of efficiency that the voltage regulator provide. And also if your circuit need a various kind of the protections against the current and other things, and very precise number of very precise voltage regulation, then Zener diode failed to do so. But if you use the voltage regulator, then it also comes with a few challenges. Like if you use the voltage regulator, then you have to add few more component with it. By like if in the Zener diode it provide you the simplicity. You just need a diode and the resistor. But if you use a voltage regulator, you need the voltage regulator IC. Then you also might need some resistors and the capacitor on the both side for its working. So there is that is another challenge for the circuit. And third is the size. uh, uh, there are lots of voltage regulators are there in the market that comes in very small size. But uh, with compared to the Zener diode, what you need to regulate once a small very tiny size Zener diode and the very tiny size resistor. But in the IC they are slightly large compared with the Zener diode. So and you also need to add the capacitor. So it's the overall size of the thing, overall size of the circuit might increase if you use the voltage regulator. So these are the few challenges that you face in the both of the circuit.
Mhm. So, how does the load and line regulation of a Zener diode compare to that of a voltage regulator IC?
Actually, load and line regulations are the very critical parameters for improving the quality of the power supply. As you know, that the load regulation is nothing but it is the ability of a voltage regulator to maintain the constant output voltage despite of change in the load current. Means load regulation give you assurance that its output is a constant output. In case of a Zener diode power supply, the load regulations is generally poorer compared to the voltage regulator ICs. As the load current varies, the output voltage can fluctuate significantly because the Zener diode's voltage drop can change slightly with the current. Similarly, another is a series resistor with the Zener diode can cause the voltage drop that varies with the load current, affecting the stability of the output voltage. And third one is the best suited for the application with the relatively constant and low current operation. These are the load regulations, the merits you may say for the Zener diode power supply. While in case of the voltage regulator, the load regulations are significantly better. Voltage regulator ICs, both linear as well as switching ICs, are designed to maintain a stable output voltage across the wide range of the load current. And it utilizes feedback control to adjust the output and the compensate for change in the load, maintaining a constant output voltage. And another one is a suitable for application requiring precise voltage regulation. Means, so you may say कि load regulation in the voltage regulator is better than the linear diode based power supply. And come on the another point, line regulation. And it's referred to the ability of the voltage regulator to maintain a constant output voltage despite change in the input voltage. Means line regulation means you will always get a constant power supply instead of changing in the input voltage. In case of Zener diode, the line regulations is relatively poor, as well as in the load regulation also very poor. So in this case, line regulation is very poor. Change in the input voltage can significantly change in the output voltage, as Zener diodes' ability to maintain a stable voltage is limited by the resistor Zener combination. Limited, and the series resistors cannot compensate the input voltage variation effectively, leading to the less stable output. And for another line regulation in the general diode power supplies is it is not suitable for the situation with a significant input voltage fluctuation. If there is a voltage input voltage fluctuation, then it is not suitable for the line regulations. While in case of the voltage regulators, line regulations are better comparatively the general diodes line regulation. In this case, it is a superior than that one. Voltage regulator ICs are designed to maintain a stable output despite variation in the input voltage. Suppose you are using 7805 and its input range is from 7.5 volt to 15 volt, 16 volt. Then if its input voltage is 8, then output remains 5 voltage. So it is ineffective by the changing in the input voltage. Another is it incorporates internal circuitry to adjust the output in response to change in the input voltages. And wide input range suitable for the application where the input voltage may vary widely, ensuring a stable and precise output voltage. So in brief, you may say, in case of the Zener diode, load regulation are poor, voltage variation with the changing in the load current, poorer performance is the significant output variation with the changing in the input, suitable for the simple low power and the load condition. And in case of the voltage regulators, in brief you may say it is excellent performance with the minimum output voltage variation over a wide range of the load current, excellent performance with the minimum power output voltage variations over a wide range of input voltage, and ideal for the application requiring precise, stable and reliable voltage regulations. And these are the basic differences between the line regulation and load regulations.
Okay, so describe a situation where you might choose a Zener diode over a voltage regulator IC for design a project.
Yeah, it is a excellent question. So in most of the scenario, you might always choose the voltage regulator because it's give you the wider range, the more efficiency, and there are lots of other functions like overcurrent protection, the heat management system, and all those things that the voltage regulators carry as an advantage. But there are various scenario where you still choose to use the Zener diode in the circuit, and it's best to use the Zener diode in the circuit for the regulation. So suppose that I want a very simple circuit, very small circuit, where I don't need very much of precise voltage regulation. My need is not that much of precise voltage regulation in my circuit, and my circuit need to be very simple and very low cost and compact as well. And then in such a scenario, it's better to use the Zener diode because uh, you don't need a high precision of voltage regulation in the circuit. That's no need to use the voltage regulator IC. Then again, your circuit didn't going to be used in the high temperature fluctuation, very high temperature fluctuation. Then the Zener diode will not be affected by the temperature. So it is better to use the Zener diode. A third thing, that if your circuit need to be simple and very cost effective. You don't need want to waste a lot of money on the capacitors and the voltage regulator IC. Then you simply buy a one resistor and the Zener diode from the market and add it to the circuit and regulate your voltage and use it in the circuit. So where you need the less cost, very simple circuit where precise, very precise regulation is not needed. The wider range of regulation is not needed. It's best to use the Zener diode because it's very simple, just a diode and the resistor in such a case.
So, what are some common applications where Zener diode are still widely used despite the availability of more sophisticated regulator ICs?
Yeah, most of the where we use the Zener diode is very in very simple circuits, DIY kind of circuit where the precision is not needed, where the wider range is not needed. Sometimes prototyping with the Zener diode because you don't need to buy a voltage regulator. You don't want to buy invest money in the voltage regulator, different voltage regulators for your prototyping. You can simply buy one of the Zener diode and start putting with the different Zener diode to prototype your circuit according to the need of the voltage, thing, voltage regulation thing. Third is the over voltage protection. They can be used as can be used as the over voltage protection in the circuits that when the voltage is very high. In such a case, Zener diode can be a good example for the over voltage protection. So these are the things where you can use the Zener diode over the voltage regulator, and these Zener diode will be best for in such huge cases.
Okay. So, what impact does temperature have on performance of Zener diode and voltage regulator ICs?
Actually, temperature has a significant impact on the performance of the general diode. It impacts on the temperature coefficient, voltage stability, thermal runaway, power dissipation. Also, these impacts are also on the voltage regulator ICs. Means it also has a temperature coefficient, thermal protection efficiency, and dissipation. But in case of Zener diode, temperature can significantly affect the breakdown voltage, leading to stability issues. In case of Zener diode, prone to thermal runaway in high current application without proper heat management, because in the Zener diode power supply there is no method of using the heat sink. Another is the power dissipation capability decrease with the increasing the temperature. While in case of the voltage regulator generally have better temperature stability, because in this voltage regulator we use a heat sink. So heat dissipates. So it it has a better temperature stability and the precision due to the design and the internal compensation mechanism. So if you are drawing more current in case of voltage regulator, then it automatically thermal shutdown. It includes thermal protection feature to enhance the reliability. Performance can be affected by the temperature, but proper heat sinking and the designing can mitigate these effects. So in brief, you may say that both Zener diode and the voltage regulated ICs are impacted by the temperature. Voltage regulator ICs are typically more robust and better equipped to handle the temperature variation due to built-in protection features and more advanced design. While in case of Zener diode based, it has less impact on these
Okay, so could you explain any new developments in the field of voltage regulation that might influence the choice between Zener diode and voltage regulator ICs?
Yes. The field of voltage regulation has seen several new developments and advancements that can influence the choices between Zener diode and voltage regulated ICs, such as the advanced switching regulators, higher efficiency based, integrated FET field effect transistor based, and second one is a low dropout regulators also come. Ultra low power dropouts voltage regulators are also available. Some voltage regulators are TO220 package, some are TO092 like a small transistor BC547, small for low current. So low dropout voltage regulators are also. Ultra low dropout voltage regulators are also available, which maintains the quiescent current reduction. New LDO designs have significantly reduced quiescent current. The current consumed when the regulators is not supplying the load current. And third one is a digital voltage regulators. And this is also programmable regulators is also coming in the market. Digital to programmable voltage regulators allow precise control over the voltage through the digital interference I2C, SPI, etc. And remote sensing and monitoring. And these are the new technologies. First and fourth one is a wide band gap semiconductors is also available. जैसे ZAN and SiC technologies, gallium nitrate GaN and silicon carbide SiC semiconductors have been introduced into the voltage regulators, affecting superior performance over this one. And another one is a enhanced protection features is also available in modern voltage regulators. In this one is modern voltage regulator ICs come with the enhanced protection feature such as more advanced overcurrent, overvoltage, thermal shutdown, and short circuit protection facilities are also available in the modern voltage regulators. Another one is power density and minimization. Advancement in the package and the materials have increased the power density of the voltage regulators, allowing more power handling in a smaller package. This is the power density and another one is the 3D packaging. New development is a 3D packaging voltage techniques stacks components vertically, saving space and improving thermal performance. So, in brief, you may say the given advantage voltage regulator ICs have become even more compelling compared to the Zener diodes, such as the efficiency, protection and flexibility, protection and reliability, and higher power density and 3D packaging along the more compact and efficient design. While Zener diode still have their place in a simple, lower power and cost sensitive applications. Modern voltage regulators ICs are increasingly preferred in some scenario requiring efficiency, precision, reliability, and the compactness due to these technologies advancement. That's all.
Okay, so what challenges might you encounter when implementing Zener diodes in high performance voltage regulator scenarios, and how would you address them?
So there are various challenges when you use the Zener diode in the. Can you repeat the question once again?
Yeah, yeah, sure. What challenges might you encounter when implementing Zener diodes in high performance voltage regulation scenarios, and how would you address them?
Yeah, the various challenges that you face in the Zener diode implementation is one of the range. then the precision and stability, and another is the temperature effect. So suppose that if you are using the Zener diode, still using the Zener diode where you need the high precision, then it will very challenges for you. You have to think about the, think about the temperature around it, around the Zener diode. Temperature change around the Zener diode should not be so much so much high and low, because if the temperature change is very frequent around the Zener diode, then it causes the noise in the regulation, and it affect the overall efficiency of the whole system. Second is the power dissipation. Zener diode often dissipate the power, and also in form of the heat, and it also, affect the overall efficiency of the circuit. So this is the second thing that you need to tackle in your design. And you have to provide certain a certain range of the design implementation and some tweaking in the circuits to tackle this. And second is the limited voltage range. When you use a diode, it don't provide you the larger range like the voltage regulator IC. So you have to keep the circuit, you have to design the circuit around the Zener diode based voltage regulators, that your circuit work around the range that is provided by the Zener diode. So Zener diode range, that in this range your circuit is able to work, and it will not fail without it will not create any problem. So you have to design the circuit accordingly when you use the Zener, still use the Zener diode instead of using the voltage regulator. Third is the thermal effect, that you have to tackle the thermal effect on the Zener diode. You might provide some kind of protections layer of the on the Zener diode, so that it will not be affected by the surrounding heat, and it will remains in around its working range, and it will not create some noise in the fluctuation of the temperature. So you have to think about around the you have to make the casing of the whole device accordingly. You have to make the what say you have to you have to make sure that the temperature didn't change around the Zener diode so much frequently, and you have to make the design according to that. Like you can use the different kinds of insulative case for the circuit that didn't allow so much heat to pass through in and out of the circuit, so that you will able to protect the Zener diode from the outer change in the temperature. So these are the things that you have to tackle, and these are the things these are the things on which that you can tackle according to the design need and according to your circuit.
Okay, so how do you determine the necessary specifications for a voltage regulator IC in a complex electronic circuit?
Actually, actually, determining the necessary specifications for a voltage regulator IC in a complex electronic system involve several steps, such as understand system requirement. We have to know what is your system requirement, such as the voltage level, current requirements, etc. And second one, you need to regulation type, which type of regulator you want to use, linear or switching or buck boost type of. So you should know the regulation type. And third one is the efficiency, power efficiency. You have to measure कि for system which where power efficiency is crucial, battery powered devices, switching regulators, etc. You need in consideration of the efficiency. And fourth one is the thermal management. You have to consider this is also the power dissipation. Calculate the power dissipation using the different formulas. And next one is a load regulation and line regulation. You have to consider, evaluate how well a regulator maintain, maintain the output voltage with varying load current. Line regulation assess how well the regulators maintain the output voltage, etc. And sixth one is a transient response. What is the transient response? You have to check the regulator's response time, rapid change in the load or input voltages, etc. Seventh one is the noise and ripple. This is very important and determine the acceptable level of output voltage with noise and ripple for your systems. Low ripple is a very good power supply, so you have to consider this one. Additional feature if you want to, such as protection feature, soft start and enable disable feature, so you have to also consider this one. And physical constraint means package type, which package you want to use, pin configurations, which type of pins configurations you want to use, and these are the parameters which you have to consider. And next one is environmental conditions, the temperature range, how much temperature it can sustain, ensure the regulators can operate with the environmental temperature range expected in your application. Humidity is also another parameter. Next is a regulatory compliances, standard and certification. Ensure the chosen voltage regulators complies with any industry standards and the certifications required for your protection. So, by carrying these consideration points, factors, you can select the voltage regulator ICs that meets the specific needs of your complex electronic system, ensuring reliable and efficient operations.
So, discuss a scenario where you successfully integrated a voltage regulator IC into a product, and what are the key outcomes?
For consideration of the scenario involving the development of the portable medical devices, such as handheld diagnosis tool, in this project, the key outcomes from the successful integrating a device, a voltage regulator IC, were reliability, efficiency, and compliance for the medical standards. Scenario portable medical diagnosis tool means project background. You have to consider what is the background of the project. Project involved designing a portable diagnostic tool capable of measuring vital signs such as heart rate, blood pressure, and oxygen levels. The device needed to be lightweight, have a long battery life, and meet stand medical standards for accuracy and the reliability. For this, you have to follow the following challenges such as power efficiency, voltage stability, size constraints, and noise reductions. Another is taken to integrate the voltage regulator IC's requirement. Input voltage should be less, means suppose as 0 to 4.2 volt typically, uh, such as the line-ion battery. Output voltage 3.3 volt for microcontroller and others. Choosing the regulator type, low dropout voltage you have to consider. Component selection selected as LT1763 LDO regulator from the linear technology, etc. Thermal management is also very important. You have to calculate the power dissipation. Testing and validation conducted load regulation test to verify the output remained stable under varying loads. Compliances and certification is also very important in this case. So you can say key outcomes are the enhanced reliability, improved power efficiency, thermal stability, regulatory compliances. This device possesses all necessary regulatory certification for the medical devices. Another one is a customer satisfaction. When you are using a medical components, then the end product met user expectation for the reliable, portable diagnostic tool with the extended battery life, with, which was the crucial for the healthcare professional in field. This successful Integration of the voltage regulator IC was vital in achieving a high performance, reliable, and compliant medical devices, highlighting the importance of the careful component selection and through testing in the product development. That's
Okay, so in terms of reliability and durability, how do Zener diode and voltage regulator ICs compare in industrial applications?
So in the industrial application, if you look in the industrial applications, so in the industrial environment, the fluctuations of the voltage and the temperature is very high. Because in the industry, in the factory, you have the boilers, vessels that often evaporates the water, high temperature water vapors. The humidity, the fluctuation of humidity is very high. And the third is the compliance. The industrial designs need high standards and compliances and regulatory compliance. You have to pass through certain certain range of uh, certification and testing things for the industrial applications. So when you use is voltage regulation in the industrial applications, of these industrial devices also need a very high precision of the voltage regulation. They need very high precision. These devices often need very high precision, and you have to get this high precision in very challenging environment. Like you need a very high precision of output voltage in the regulated voltage, while there is still very high fluctuation in the temperature, humidity around the environment, in the industrial environment. So when you get in this in when you get your device in this industrial environment, then if your device is using the Zener diode, suppose that let's take both examples. So also suppose that my design use the Zener diode, then in the industrial application, if we need a very high precision, these diodes will not able to provide that high precision. And the second scenario, if we go in the industrial areas, they have the boilers, they have the coolers, they have the different kind of equipment in the factory. There are lots of heat dissipation, the fluctuation of heat, humidity, and various gases and many other things are there in the factories and in the streets. So these fluctuations are a lot. So when the Zener diode exposed to these things, these fluctuation of the temperature, fluctuation of the humidity, they often fail to provide the precise regulation. So Zener diode often fails to provide you the efficiency in the industrial environment. They often fail to give you the precise regulation in the industrial environment, and they often fail to also comply with the regulatories and the certifications things. But if you look into the voltage regulators ICs, so there are various voltage regulator IC that you can choose between the range of this voltage regulator IC that is made for the industrial application, that is pre-certified. They are pre-certified with the for certain industrial applications, certain applications. They are pre-certified with ROHS environmental certifications. They are pre-certified. So you not need to think about those certification if you include those regulators in the IC when it comes for the industrial design. And second thing, in the industrial design, like I have already told you, the fluctuation of the temperature, the fluctuation of the humidity, the fluctuation of the outer environment is very high. In such a case, there are the voltage regulators that are especially designed for that. These chips are especially designed to regulate itself according to the changes, and it's still able to provide you the high precision. So voltage regulator by default, the voltage regulator gives you high precision when you compare it with the Zener diode. But there are various ICs that are especially made for the industrial application that didn't get affected by the fluctuation of the environment, humidity, and other things. So these are the two different factors that affect in your design, and that makes you to choose makes you to think that that the voltage regulator ICs are better choices for the industrial application, because you have the you have the very wide range of the regulation, the precise regulation, and the immunity towards the environmental change, and immunity toward the towards towards sustain in the frequent change of temperature, humidity, and various environmental factors. And third is the vibration things. So if you're in industrial application, there are certain industrial application where the things vibrate a lot, like you have mounted the circuit on the large cooler, or you have mounted the circuit on some kind of testing equipment, some motors around it, so it's often create the vibration around the circuit. So in such vibration, when any circuit vibrates, then efficiency always decreases accordingly. So but and you have to consider that these vibrations as a important factors into the design when you using the industrial design, because these vibrations often reduce the efficiency and durability of the overall circuit. So if and third is the failure point. So let me tell you what are the failure points. So there are various points at which your device might fail. So the more the number of equipment that you add in the device, the more the failure point will increase. The more the connection points increases in the any circuit, the more the failure points will be increased. So suppose that I have a circuit and I have a diode, and then I have a resistor, then I add another resistor, then I add another resistor. So what are the total failure points in the whole circuits? First is the diode, then the resistor, then I have another capacitor, then the resistor, then another capacitor. So our one failure point is the diode might get failed. The second failure point is the capacitor might get failed. The third failure point is the resistor might get failed. So the failure point will be increased with each and every component you add in the circuit, and that one of the circuit might fail and the whole circuit become unusable. So this is the another consideration in the industrial environment. So if you increase the failure point in the whole circuit design, then if there is a high vibration and environmental change around the circuit, then these failure points is the very very uh, very challenging things for the durability, very challenging thing for the durability of the whole circuits, because any of the individual component will fail and the whole circuit will be turned off. So you have to think about these things as well. So but in the Zener diode circuit, it gives you the less point of failure because we have just a diode on the circuit. In the voltage regulator, it offers you the more failure point, because with the IC you also need some capacitors, so the more failure points are there. But if you think about the compliance and regulatory, then these ICs you will get the pre-certified ICs and pre-certified ICs in the market that will able to pass the industrial compliances and the certifications. But while if you use the Zener diode, then you have to recertify the whole things, whole circuit after designing the voltage regulator on the Zener diode. So this is the another thing that makes you to use the voltage regulator over the Zener diode. So overall, the voltage regulator are more reliable and more durable and more efficient in the industrial environment and in the industrial design, because they offer you the overcurrent protection, the larger range of voltage things and all those things. And then another thing that the voltage regulator, using the voltage regulator in the industrial design, that you face using the voltage regulator in the industrial design, most of the industrial design or some of the industrial design need very high range of current and very high range of the voltage. So when you go for the ICs that give provide you very high range of current and very high range of voltage output, then they often dissipate a lot of heat, and you have to make up, you have to add what say the heat sink on the voltage regulator. You might have seen various when you open might have seen when you open the industrial components, might have seen the heat sinks behind uh, behind the voltage regulator. So heat sink might need the heat sink of thermal management in the overall PCB or overall circuit. So these are the things. But overall, if you ask me for the conclusion, then voltage regulator is the best choice for the industrial application, because they are more durable, more reliable, and they offer you more more immunity towards the change industrial environment.
Okay, so what software tools tools do you use for modeling and simulating voltage regulation components during the design phase?
Yeah, there are various tools are available. One is the there are various tools for the modeling and designing for those the for modeling and the simulation for the design phases. There are different for the various designs and various need according to your need. One is the spice based simulation tool, that is LT spice. Another is the P spice. So LT Spice is developed by the analog devices, and it is widely used for the simulation tool for high efficiency simulation in the analog circuit. And then is another the P Spice. So and for the PCB layout, the overall PCB layout, the calculating the area and designing the voltage regulators based on the Zener diode or IC on the PCB. Then there are the tools like Altium, the Eagle, the KiCad, and there are other tools are there in the market. And for the simulation level, there is a MATLAB. You can use the multi simulation. You can use for those things. So for the industrial application, there are tools like LT Spice, P Spice are available. For the PCB designing of the voltage regulators, the tools are available for the LTM, Eagle, KiCad, EGEDA, and similar EGEDA is not KiCad and EGEDA are the open source tools for the PCB design for the voltage regulators, while the LTM and Eagle are the more give you the more more functions, give you the function of design the flexible PCBs, and give you the flexibility on the designing the case over the whole circuit. So but while the KiCad and EGEDA give you the are the open source, they are the free tools. So you can choose in between for the PCB design. And for the simulation you can use the MATLAB, multisim, and other thing. For the and for the industrial kind of simulation, I have already told you, you can use the LT Spice by the analog devices or PSpice. So these are the simulation tools and other things that you can use.
Okay, so my last question for today. What innovative techniques are you aware of or have implemented to enhance the performance of the standard regulation components in your project?
So in my experience, I generally use the I generally use the voltage regulators, but sometimes I also use the Zener diode for the regulation, where I did not need much precision and not need the much much range in the circuit for the regulation. And suppose that if I am using the Zener diode for the voltage regulation, but the temperature is a key factors for such scenario, then I usually try to make a case as usually try to isolate the circuit, the whole PCB from the outer change. I try to insulate the whole circuit from the outer change, so that outer environment, outer change in the temperature will not affect the inner circuit and inner Zener diode to that affects the and that adds the noise in the voltage regulation. This is a thing. And I invite the Suresh sir to, if he have if he have any more ideas that he have used in the this year of design experience, then he can also share.
Hello. For designing in this case, so voltage regulator ICs are the more efficient compared to the general diode, because you can use them for better efficiency, you can use the heat sink, and you have a proper control over it. But in case of general diode, you can't control it, neither for the temperature nor the current limiting. So there is a certain environmental effects is more on the general diode based power supply. But in case of the voltage regulators, environmental effects are very less. So We recommend that the Zener Diode IC power supplies are less full for the precise projects. So you need to use the voltage regulators power supply. That's all.
Okay, great. So, thank you for your time, and we hope this discussion was helpful for you. And if you have any questions regarding this topic, do write a question in comment section. We'll get back to you in the next episode. Thank you.
Thank you. Thank you, everyone.
Thank you, everyone.